Welcome to ES 310 Lesson 19. Today's we're going to be focusing on finding the velocity of a rigid body subjected to planar motion using relative velocity methods. We will look at generic cases of this, and then we will look at using an instantaneous center of zero velocity to simplify this analysis. More information about this topic can be found in Hibbeler's Dynamics text, Chapter 16, Sections 5 and 6. The topics for today are linked to the topics from last lesson, so we need to probably review a little bit of what we looked at last lesson. So we started rigid body motion last time, and we looked at both translation and rotation. So in translation, we have a relationship between the position of a point B being equal to the position of point A plus the relative position between point B and point A. And then if we take the time derivatives of that, we find that the velocity of point A and B are the same, and the acceleration of point A and B are the same. So a general translation has any line staying in the same orientation but moving along a curve or a straight line. In rotation, we have a series of new variables. So we have omega, which corresponds to speed, rotational speed. We have theta, which corresponds to rotational position or angle. And we have alpha, which corresponds to rotational acceleration. The equations, the kinematic equations, are the same as they were with the linear variables. So we have the time derivative of the position equal to the velocity, time derivative of the velocity equal to the acceleration. This combined equation, right? So alpha d theta is equal to omega d omega. And we have, if we have constant acceleration, we have the constant acceleration kinematic equations. We can relate rotation to linear motion through the geometry that says that the arc length is equal to r times the enclosed angle. Taking derivatives of that, then we have the velocity is equal to omega crossed with rp, and we have the acceleration is equal to the tangential part plus the normal part, which gives us tangential is alpha crossed with r, and the normal part is omega squared times r negative. We also looked then at finding velocity relative to a fixed point, which was a translation plus a rotation, and we related our translation and rotation through geometry and found derivatives. So today we're going to extend this to include problems which don't have a fixed point. So to do that, we take a look at the position. This equation has not changed, right? So the position of B is equal to the position of A plus the position of B relative to A. So remember, this notation gives us the position of B as measured from A. The displacement then is a change in position. So the change due to translation and rotation of B is equal to the change due to the translation of A, because A is moving, plus the change of position due to the rotation around A. So we pick a point, that point is moving, that gives us dr dA, or dRA, and the body is rotating around that point, which gives us dRB with respect to A. The velocity then is VB is equal to VA plus VB with respect to A. And VB with respect to A is omega crossed with R. So this is again rotation, right? And this is translation. So the procedure here in general is on whatever diagram we're looking at, we're going to identify point A and B. We're going to identify the omega if we know it, and we're going to identify the distance r of B from A. All right, so that's our notation there. We're going to define our directions for velocity of A and velocity of B and omega. And then we're going to apply our vector description of the velocity of b. This is actually two equations, right? It looks like one, but there's an I hat part and a j hat part of each of these terms, so we can break this into two equations of i's and j's, and then we can solve. So we can solve for up to two unknowns using this equation. If we pick the right a and b, things get a whole lot simpler. So for one thing, you're going to pick the point that you're interested in. If you're asked about information about point B had better be in your equation. You also want to pick a point that you know something about. So some common points that you want to pick. If something is rolling, we know that the center of the thing that is rolling is moving parallel to the surface. The point of contact of something that is rolling is moving with the surface it's in contact with. So if it's rolling on the ground and the ground itself isn't moving, then v is equal to 0 at the point of contact. In some cases, the motion is constrained. For example, A is constrained to move horizontally, right? And so we know it only has an I part. It doesn't have a J part. And points on rotating bars move along a circle. So point B, which is a rotating bar on BC, moves along a circle. And so we know that the velocity is tangential to that circle. And so we have a direction of that velocity based on whatever angle we're at. And so by picking one of those points, we have more information than just a magnitude to feed into this equation, because we have information about direction as well. So let's take an example of this. In this case, we have a gear rack down here at C that is moving with a velocity of 5 to the left, and that is causing the gear itself to rotate, and the gear is rotating at an omega of 10 negative, right? If we use our right hand rule, our thumb goes in, so this would be a negative omega. And our goal is to figure out what the slider is doing. The slider has to move up and down, right? It's constrained to move up and down. So let's start by looking at the gear. If we look at the gear itself, we have a middle point that I'm going to call M. And that is where the end of this rod, which was what we're going to look at next, is attached. So we're looking at the gear, and we're going to write our V equation. So we're going to look at the 2 points we're going to look at are M and C. So we've got Vm vector is equal to Vc vector plus omega crossed with R of M measured from C. And all of those are vectors. So now we can fill some of these in. Point C is in contact with the gear track, right? So point C must be moving to the left with a velocity of 5. So just as a reminder, this is the positive I hat, that's the positive J hat. So VC is negative 5 I hat. Omega is in the K direction, and it is negative. We talked about that from our right hand rule. So negative 10 K hat crossed with R of M, the position of M as measured from C, so that is this distance, right, going up, so it's going to be positive, and the radius is 75 millimeters, so 0.075 J hat positive. If we take this cross product, K, which comes out of the page, crossed into negative K, which goes into the page, crossed into positive J, which points up, gives us a positive I hat direction. So the way I did that was I used my right hand rule, put my fingers along the negative K direction, so point my fingers into the page, bend my fingers to the positive J direction, so up, and my thumb points in the direction of the cross product, which is to the right, so the positive I hat. So this gives us negative 5 I hat plus positive 10 times 0.075 I hat. So the direction of this quantity came from the right-hand rule cross product of K and J. So then we can add those together and we get negative 4.25 I hat being the direction of VM. And VM is on the center of something that is rolling, and so we expect it to be parallel to to the surface it's rolling on. So we did expect it to be in the I hat direction. All right, so now we know the velocity of point M. We want to find the velocity of the other point at the other end of that rod at point A. So we need, this rod is also going to be rotating. So I'm going to draw that as omega B of the bar. We're interested in the point where the angle is 60. So now we're going to look at the bar. The 2 points we're interested on the bar are M and A. So we're going to do VA, which is what we're looking for, is equal to VM, we know that, plus omega crossed with RAM. So this is omega of the bar, and this is the position of A as measured from M. So if we fill these in, we know VM, that's negative 4.25 I hat. Omega B we do not know, but we do know it's in the K direction. So, and it's in the negative K direction the way I drew it. So it'll be negative omega B K hat crossed with R of A relative to M. So if we draw our R up the bar, we can write that as the length of the bar is 0.5. The I hat direction is in the negative direction, and it is the cosine of 60 because it's adjacent to the angle. That's I hat plus 0.5 sine of 60 J hat, and that's positive, it's going upwards. So that's our R. Now we need to split this, and we know VA is also acting only in the J direction. So we have VA J hat. Now we can split this into two equations. Well, first of all, let's take this cross product. So we get negative 4.25 I hat, negative omega B K hat crossed into negative J hat. So negative K hat goes into the board, or fingers go into the page. We cross into negative J, so we bend those fingers to the right. Our thumb points up, so it's a positive J hat answer. So that's going to be positive omega B times 0.5 cosine of 60 J hat. Now we have negative K, so into the board, fingers go into the board, crossed into a positive J, so fingers bend up, thumb points to the right, so that's a positive I hat, omega B times 0.5 sine of 60 I hat. Now we have everything outside of the cross products. We've completed the cross product, so we can look at our two equations. In the I hat direction, we have 0 is equal to negative 4.25 plus omega B times 0.5 sine 60. So that's just pulling all the I hat parts. J hat part, we have VA is equal to omega B times 0.5 cosine 60. So from the first equation, we can solve for omega B, and we get 9.815 radians per second. And we can plug omega B into the second equation and solve for VA, which gives us 2.45 meters per second, and it is positive, so it's going up. Now, that equation simplifies if we can find a point on our object or in our system where the velocity is 0, because then VA, or the V on the left-hand side, or the V on the right-hand side of the equation will be 0, and you just have V is equal to omega crossed with R. The trick is finding that point. Usually there is such a point. There's an instantaneous center somewhere. It may not be on our object. It may be somewhere else in the system. But you usually can find that IC, that instantaneous center. So how do we do that? Well, for one thing, we recognize that so our radius from our point to our point relative to our instantaneous center is going to be perpendicular to the velocity of our point. So using that, we can locate IC. So we can draw that perpendicular line to our velocity, and somewhere on that line is IC. If we know the velocity of that point and omega, then we can just divide the two. We draw the perpendicular, the length is VA divided by omega. If we know two velocities, VA and VB, we can draw the perpendicular to those two velocities. The intersection of that will be where the IC is, the instantaneous center is. If VA and VB are known and they're parallel, those would never intersect. They're on the same line. Then we can use similar triangles to figure out where IC is. So we have VA going one way, VB parallel to VA going either direction. The IC is somewhere on the line perpendicular to both of those. Connect the tips, the magnitudes of the two, and that it gives you where your IC is. So let's take a couple of examples and see how this will work. So in this example, we have a bowling ball. And the person who's bowling throws the bowling ball down the alley, and there's a backspin. So initially, the center, the whole ball is moving to the right, but it's spinning backwards. So there's actually slip happening at A. It's not rolling, it's slipping at A. And we're trying to find what is the speed of this point at A. All right, so to give us an example of this, here's a video of a pool ball, which shows backspin on it. So the pool spin is hit. You can see it's backspinning for a while, then it's sliding. We're just translating, and then it starts spinning forward. And so we're looking at the initial part of that where it's backspinning, and that is the goal, is figuring out the speed of that bottom point. So one way we could do this is to write VA is equal to VO plus omega crossed with RAO. All right, this is not using instantaneous centers of zero velocity, however. So let's try to figure out how we could do this with an instantaneous center of zero velocity. So in that case, the equation would be VA is equal to VIC plus omega crossed with RA with respect to IC. The whole point is VIC is 0. So we know that the IC, the instantaneous center, is going to be somewhere along the line perpendicular to the velocities. This velocity down here is also going to be in this direction. So if we connect these two, IC is somewhere on that dotted line. To figure out where, we're going to use the first of these two rules, right? So we're going to use this rule. That VA, if we know VA and omega, we can find the magnitude and the direction. So we're going to use VO. We know VO, we know omega. All right. So to find IC, we're going to use the information about VO that we've been given. So we can also write the equation that VO is equal to VIC is plus omega crossed with ROIC. And so VIC is 0. We get VO, which is 8, positive I hat direction, is equal to omega, which is 10 in the positive K hat direction, crossed with ROIC, which is, we're going to say positive. So we're trying to find this distance up to wherever this IC is. So this is going to be this distance in the positive J hat direction. So positive K crossed into positive J gives us negative I. All right, so fingers coming out of the page, bent to the positive j, so up direction, thumb points to the left. So negative 10 times ROIC is equal to 8, if we're just looking at the I-hats then. So ROIC is equal to negative 0.8. So the distance from IC to O is negative 8. So we start at IC, we go to O, we go downwards, that's 0.8. All right, so then R of A relative to IC is going to be the negative 0.8 plus a negative 0.12, right? Because we've got the 120 millimeters radius. We're going from IC all the way to A. So we have VA, which is in the I-hat direction, is equal to omega, so 10 k-hat direction, crossed with negative 0.8 minus 0.12 in the j-hat direction. And so we take this cross product, positive k to negative j gives us positive I. So we get 10 times 0.8 plus 0.12 I hat is equal to VA I hat. Multiply that out, you get 9.2 as VA, and that would be in meters per second. And so this is how we had to do some geometry, some extra work to find where IC is, but once we find IC, our equations are pretty simple because we no longer have this term of velocity in them. So here's another example where finding IC, finding the instantaneous center of zero velocity would be useful. So we have a stick with a wheel on it that's sliding down. So the wheel is rolling outwards, so it's moving at a speed in the I direction. The speed of this point B is going to be along the beam or along the rock. Okay. As it does this, it's got some omega, and we're supposed to figure out what is the speed at point C. So we want to do this by finding center of zero velocity. So we know that those are perpendicular to the velocities. So we have the directions of two of the velocities. Let's draw the two perpendiculars. So there's this one, and there's this one. So these are perpendicular in both cases. If this is 60 degrees, then this angle in here is 30 degrees. And so then the question is, can we figure out where this point where they intersect is IC? So looking at some numbers here, we have this triangle down here, right? We have the height is 4. We have this angle of 60, so the length here, L, is equal to, well, let's see. So the leg 4 is equal to the hypotenuse L times its opposite, so sine of 60, which gives us L is equal to 4.6188. All right, then we look at the next triangle. L is the leg of this one, and this here, which is R of A relative to IC, and that would be a negative number going down, right? So the position of A as measured from IC is this distance. That's the hypotenuse in another right triangle. And so the leg, which is L, is equal to the hypotenuse, RAIC, times, in case it's adjacent to the 60, so cosine of 30, which gives us that RAIC is equal to, the magnitude of it is equal to 5.33. Remember, the direction will be negative. All right, so now we know where RAC is relative to A. Can we find, we're looking for RC, so we need to find where is IC relative to C. So what is this side. This is R of C relative to IC. It may or may not be straight across, right? Rod is left to fall. So we now have another triangle, right? We've got the length 6, the angle 30. So since this may not be straight across, we cannot assume that this angle is a right angle. So we're going to have to use the law of sines or cosines in order to find our CIC. So in this case, we know one angle and two sides, so we can use the law of cosines. So we have that R of C relative to IC squared is equal to R of A, right, this side, relative to IC squared, plus 6 squared, that's the other side of the triangle, minus 2 times 6 times RAIC times cosine of 30. So we know RAIC, that's the 5.3. So we know all of these things, so we can solve this and we get that RCIC at the point where this angle is 60, that angle is 30, is equal to 3. So now we can go over here and write out our relative velocity equations. So to figure out omega, we need to have a known velocity. So we're going to use the VA, which is known. So we'll start with that equation. We have that VA is equal to VIC plus omega crossed with R of A relative to IC. So if we write these out, this is 6 I hat, that's positive, this is 0. Omega is what we're looking for, but we know it's in the K direction. Crossed with RAC, which is 5.33, and we said that was negative, right? The position of A relative to IC, and that's negative J hat direction. Take this cross product, K is coming out of the board, negative J goes down, gives us a positive I hat, so 6 is equal to omega times 5.33, gives us an omega of 1.125. Now that we know omega, we can use it and the known position, RCIC, to find the velocity at C. So VC is equal to VIC plus omega crossed with RCIC. So in that case, then VC is what we're trying to find, is equal to 0 plus omega, which is 1.125 I hat, no K hat, crossed with RIC. The magnitude of RIC is 3. The direction of this is going to be perpendicular to this line, right? At whatever point it's at. The magnitude of it, if we just use the magnitude, we get 1.125 times 3, which gives us a magnitude of 3.38 feet per second. We could find its direction as well by using the angles in this triangle to determine sines and cosine components of that arrow.